Welcome to the Birck Nanotechnology Center. I'm Ali Shakouri, director of the Birck Center. This is a collaborative research facility. We are home to the main clean room for the university, and you will see it in a little bit. It's about 187,000 square feet building with 25,000 square feet of clean room facilities. We have 200 graduate students that are resident. They come from 57 research groups from 15 different academic units. As you know, for a lot of these smart city, smart community challenges, we need to bring different disciplines together. Here we have students from engineering, electrical, mechanical, chemical, materials, biomedical, as well as agricultural engineering, food science, pharmacy, physics, chemistry, biology, so you name it. And being on under the same roof and using the labs, that's really what creates a community where collaborations can flourish. So what I'm going to describe is the work that we have been doing on smart films. You have a brochure on a smart industry consortium. We started in 2016. All of you have wonderful smartphones. They are great for talking, but you also know how much they cost. One of the areas for IoT technology for ag and also many other applications is very low-cost sensors. So here is an example of in farms. The box here you see is an electronic box, which is shown here. And what you see in the box is actually, it's good people who know how to handle it open it up. It's actually radios that we use that has LoRaWAN, it has Bluetooth, and this is communication not too different from what is inside your phones. But what this doesn't do is measuring local chemistry of the soil, of the water, biological activity. So our main activity here is how to make low-cost sensors. If you can, so this is actually a live website. You have access to it, and you can click maybe on a device. You can see that what is there. What we are doing here, this is the example of the smart films. And we will go upstairs and you will see how this is actually made. It's a printing technology, not that different from what the printers you have in your office, but it's a functional printing. And with this, we can make devices that measure nitrate, phosphate, microbial activity. This is quite important for agricultural productivity. But other applications we have are in area of healthcare, wearable devices. It may not be the most exciting title, but we have a smart diaper that measures urinal infection and send the data to the nurse when there is a problem. We have smart wound dressing that can help. So it's not only sensing. We are able to make printed devices that locally generate oxygen and or even ozone for some of the healthcare applications. So here what you see are real-time data. You can see the map. This is actually Birck Center, and this is the device that is sitting here. And it shows the temperature and humidity, nothing special in the last couple of days, or actually a couple of hours.
It's actually showing it real time every 30 minutes or so.
Every 30 minutes, but it can be programmed. You can measure it every minute, or you can measure it every day. One of the key things about anything related to IoT in ag is power consumption. The box and the sensors are designed so that with the standard batteries, they last a couple of years. The box, of course, is reusable, but the important thing is that these sensors can be made from substrate and ink materials that are fully biodegradable. That's quite important. You don't want the farmers to go and try to find them. I don't know what else on the pictures you want to show.
The other set of deployments is the manufacturing network deployments.
So what we have on the manufacturing, similar type of sensors we use to monitor manufacturing equipment. By the way, when we call manufacturing, a lot of farmers have grain elevators and other processing equipment, how you monitor them. And here are on a map locations that we have it. This is the location of Purdue. You can see a couple of locations. We have about dozens of deployments for ag and a dozen for manufacturing. Maybe you can show one of them.
So some of these locations are restricted access, but some of them, like for example at IMI is an open source one.
So actually, the IMI facility is your last stop of the tour. So this is advertisements, so you stay until the end. What you have at that facility is industrial scale machining tools, and we have sensors that measure vibration, sound, and local machine properties, and again, fetch it out. It will take a little while, but you can see. So this is actually a machine that when you go there and you visit it, again, real-time access. Some of it is in a real manufacturing facility, and of course, they don't want people to know how busy they are and what they are making, so that is password protected. What I will do next is that I will show you actually how we make some of these sensors, and I will be glad to answer if you have any questions. Thank you, I really appreciate it. Currently, with the current manufacturing, which is not, production scale, still we have sensors that cost about 7 cents each. And, but the plan is when you bring the speed of manufacturing higher, you can print them as you print newspapers. The way you bring the cost of roll-to-roll manufacturing is to make things fast. We think we can bring them to a fraction of a cent, and that's really the idea. And again, we don't have time for lots of different sensors. The idea of having a low-cost sensor that is disposable, very low cost, works for a couple of weeks to a couple of months, and you throw it away or decomposes is one way. But still, the radio is something you have to pay, and could break down. We have had accidents, the tractor hits the box and things like that. But we do have fully biodegradable sensors that are passive. They work like an RFID key, like the key you have for your home. They are under the soil. They can work at the depth of a couple of inches, and you bring a reader nearby to read it. And okay, you don't have the reading continuously, but whenever you can send a drone to read it, you can read it, and then you don't even need to worry about the sensor itself. It decomposes. So basically, what is here is a printed electrode, and on top of it, we have an ion selective membrane. By changing the chemistry, you can measure different ions, different materials. So with the same kind of platform, we measure sodium, potassium, phosphate, nitrate, and so on. But also we have, this is what is called potentiometric sensors. They generate a tiny voltage that is proportional to the ions that are in the solution or in the soil. By the way, we get a sensitivity on the order of part per million, with the, being quite careful. But there are other sensors that we make to measure bacteria. One of the areas that Nitin was involved earlier was related to food science, and there we also measure things such as E. coli and things that for food safety as well. pH, gas sensors, ethylene. We had a project for a couple of years, measured food freshness. And again, all made using similar technology. That's one of the advantages, is you have a platform with which you can make multiple sensors. So welcome to the manufacturing site. So what you see here is a tool that was specifically designed for low-cost sensors. So here is a diagram of the tool. It's 45 feet long. Is a sheet of plastic, paper, or whatever you want comes in. Solution casting, electrospinning, melt casting, different ways to put some material, active materials on top, and then goes through laser heating. There is even some electromagnetic field alignment. I can tell you a little bit about it, and then it's cured and comes out. So the end result is what I showed you this morning, is downstairs, and that's sensors, for example, for ag. The flexibilities, you can change anything on this you want. Why this is not yet commercial is because to make these films that are very sensitive, you need to have reasonable control. So we work a lot on inline characterization and method to make the manufacturing reproducible. Here is an example of a film that the thickness is on the order of a couple of 100 microns. Each human hair is about 30 to 50 microns. Give you an idea. It's not, you can touch it. But here you can see these lines are particles of materials. It could be, in this case, piezoelectric material. So what happened is that now the material is plastic. It's deformable. You can make it to be almost transparent, but you have particles in it under pressure generate voltage, or under electricity, they vibrate. So we use this as an ultra-sensitive force sensor. You can have a feather of a bird dropping, and you can measure the voltage, and some of the posters here give you some of these measurements. So the measurement here is how the particles are made. But the interesting thing, that's the last part of the what we did with the tour, is that you see out of this we can make transparent flexible speakers. So you can make the windows of the houses for smart houses to be also a part of the speaker, or noise cancellation, and so on. What I'm not describing, of course, in addition to what is this machine, we have a suite of others. This is one example. We have half a dozen other tools, all specifically designed. What is actually behind me is one of the labs downstairs. This is actually an Injet Printer, and that's exactly the same principle of inkjet you have in your office, but it prints functional inks, and that's what we use actually for some of the sensor deployments. One thing I should emphasize, when we started this project, originally the whole idea was, this is a bottleneck, low-cost sensor, let's innovate. Once we made it, we realized, well, you need to actually get the whole vertical stack. What I mean vertical stack is that people care about data. The sensor I showed you is good, you say, wow, but at the end I need data. And to measure that data, if every time you need a student to go with a voltmeter and measure it, that's not scalable. So we really realized networking, communication, electronic needs to be solved. Data comes out. Then people can do something useful with it. At the beginning, we thought it's a burden because that part is not the interesting part of research. We buy commercial parts. We make this is our unique sauce. But now we realize, no, actually, there is an advantage. One of the things, for example, we have learned is that any sensor you put in outside environment, because it rains and it's thunderstorms and temperature variation, drifts, degrades. If I don't want it to degrade, I need to encapsulate it very well, package it, and that becomes like a $1,000 sensor. Then what's the point? The sensor itself is a cent, and then the package and everything is expensive. Now, one of the things we have done is we make low-cost array of low-cost sensors with the same electronics. All of them decay and age, but we design them to decay and age differently, and we can correct for that. And that's one of the ways we can get part per million sensitivity in an outside environment. So data analytics is actually quite helpful on the manufacturing side itself. Functional inks, example of it, for example, what you saw in my hand was silver paste. So this make conductors, but then people make proteins, functional, biological inside an ink, and that way you make a surface that captures, for example, COVID virus. We actually had people using this to make COVID sensors. So the device is still electronic, but the functional part, you need to be able to tune it, and that's the advantage of this type of technology. They are using these smart piezoelectric skins for applications as noise cancellation, but great applications for cars. Now you have something that can tell you anywhere on the car something touches. You can even measure the force of the wind and things like that. You can think about diverse applications. Submarines, they're using about ultrasounds on the skin. So basically it becomes a functional skin of any structure. Of course, you want to protect it, but underneath that protection, you can put different functionality, things that measure impact, things that measure local pressure, temperature. So there could be diverse applications. I don't know if I also mentioned one of the other areas we have worked is sensors that you can put in during manufacturing. So one of the areas we are working is sensors that are printed. You put it with a drug. As it goes through the manufacturing, each step tells you the pH. These are the quality control that can be used. And again, today, somebody could take an external device, do it by hand, but here the idea is that if it's fully disposable and embedded inside this pharmaceutical manufacturing line, then you can do quality control. So in the case where we have a sensor that generates a voltage and then we connect it to a radio, then the question could be answered by anybody with the communication, how CBRS channels interfere and so on. But for purely passive sensor, they are like tiny antennas. And we design them so that there are a different frequency range and you basically, the reader controls it. It's wide variety. Then you're not limited by communication channel, bit rate is like a scanner. And there's more flexibility.